In the cold darkness between Mars and Saturn, there exists a world so massive, so powerful, that its very existence shaped the destiny of every planet in our solar system, including our own. A world where hurricanes rage for centuries, where lightning bolts flash with the power of 1 billion thunderstorms, where an ocean of liquid metallic hydrogen generates a magnetic field that could swallow the sun itself. This is Jupiter, the king of planets. But Jupiter wasn't always the colossus we see today. 4.5 billion years ago, it didn't exist at all. There was only darkness, dust, and a dying star's final breath. This is the story of how the largest planet in our solar system came to be, how it migrated across the heavens like a cosmic wrecking ball, and how, in doing so, it may have made life on Earth possible. Our story begins approximately 4.6 billion years ago, in a region of the Milky Way galaxy that would one day become our cosmic neighborhood. Here, floating in the void between the stars, was something that looked utterly unremarkable, a giant molecular cloud. Astronomers call these structures stellar nurseries, and for good reason. They are the birthplaces of stars, vast collections of hydrogen gas, helium, and trace amounts of heavier elements, oxygen, carbon, nitrogen, iron, the ashes of ancient stars that had lived and died billions of years before. This particular cloud stretched across light years of space, cold, dark, seemingly lifeless. If you could have stood within it, an impossibility, of course, you would have seen nothing. The density of matter was so low that it made Earth's most perfect vacuum look crowded by comparison. And yet, something was about to happen. Something that would set in motion a chain of events leading to you watching this documentary on a planet called Earth, orbiting a middle-aged star we call the Sun. What triggered it? We don't know for certain. Perhaps it was the shockwave from a nearby supernova, the explosive death of a massive star. Perhaps it was the gravitational perturbation from a passing stellar system. Or perhaps it was simply the cloud's own internal dynamics, regions of slightly higher density beginning to attract surrounding material through the inexorable pull of gravity. Whatever the cause, the effect was catastrophic in the most creative sense of the word. The cloud began to collapse. As gravity pulled the gas and dust inward, something remarkable happened. The cloud began to spin. This wasn't random. Angular momentum, the tendency of rotating objects to continue rotating, meant that as the cloud contracted, it had to spin faster. Think of a figure skater pulling their arms in during a spin. The same physics that makes them rotate faster was now shaping our entire solar system. The collapsing cloud flattened into a disk, what scientists call a protoplanetary disk or solar nebula. At the center, where most of the mass accumulated, temperatures and pressures began to rise. Higher and higher, hotter and hotter. Within about 100,000 years, a blink of an eye in cosmic terms, the center had become so hot, so dense, that hydrogen atoms began to fuse together, forming helium and releasing tremendous amounts of energy. A star was born, our sun. But the story of Jupiter was only just beginning, because while the sun claimed the lion's share of the collapsing cloud, roughly 99.8% of all the mass in what would become our solar system, there was still plenty of material left over. And that material, spread throughout the spinning disk like cosmic pizza dough, held the building blocks of worlds. In the early solar system, location was everything. Close to the newborn sun, where temperatures soared to thousands of degrees, only the hardiest materials could survive in solid form. Metals like iron and nickel, rocky silicates, compounds that could withstand the searing heat. This region would eventually give birth to Mercury, Venus, Earth, and Mars, the terrestrial planets. Small, rocky, dense, But farther out, beyond a critical boundary that scientists call the frost line or snow line, something very different was happening. The frost line sat approximately where the asteroid belt is today, roughly 2.7 astronomical units from the Sun, or about 2.7 times the distance from Earth to our star. Beyond this invisible boundary, temperatures dropped low enough for something crucial to occur. Water could freeze. And not just water. Ammonia, methane, carbon dioxide, all these volatile compounds that would have evaporated instantly in the inner solar system could condense into solid ice crystals. This changed everything. You see, in the inner solar system, planets had to build themselves from relatively rare materials. Metals and rocks, while abundant compared to some elements, made up only a small fraction of the solar nebula. But beyond the frost line, planets had access to water ice, and water, composed of hydrogen and oxygen, two of the most common elements in the universe, was fantastically abundant. It's as if the inner planets were trying to build houses from gold and diamonds, while the outer planets had access to unlimited lumber and concrete. And so, in this cold, dark region of the solar nebula, approximately 5 astronomical units from the Sun, something extraordinary began to happen. Tiny particles of ice and dust, some smaller than grains of sand, began to stick together. This process, called accretion, started slowly. When two dust grains collided at gentle speeds, electrostatic forces, the same forces that make a balloon stick to a wall after you rub it on your hair, caused them to bond together. These clumps attracted other clumps. Millimeter-sized grains became centimeter-sized pebbles. Pebbles became rocks. Rocks became boulders. The process accelerated. Within just a few thousand years, objects the size of small asteroids, planetesimals, were swarming through this region of the disk. And among them, one body was growing faster than all the others. The embryo of Jupiter. Why did Jupiter's core grow so quickly? The frost line acted as a kind of cosmic traffic jam. Material falling inward from the outer solar system tended to pile up at this boundary, creating a region of enhanced density. More raw material meant faster growth. It was a case of being in exactly the right place at exactly the right time. Within about 1 million years, extraordinarily fast by planetary formation standards, Jupiter's core had grown to roughly 10 times the mass of Earth. Scientists believe Jupiter is the oldest planet in our solar system, having formed just 1 million years after the Sun itself, and roughly 50 million years before Earth even began to coalesce. And this is where things got really interesting. You see, at 10 Earth masses, something changes. The growing planet becomes massive enough that its gravity can begin capturing not just solid materials, but gas, the abundant hydrogen and helium that made up the bulk of the solar nebula. At first, this gas accretion happened slowly. The core attracted a modest atmosphere, which added to its mass, which increased its gravity, which allowed it to attract more gas. A feedback loop was beginning, but there was a tipping point. When the mass of the captured gas became roughly equal to the mass of the solid core, somewhere around 20 to 30 Earth masses, the feedback loop went into overdrive. Scientists call this runaway gas accretion, and it was spectacular. Hydrogen and helium from the surrounding disk came streaming in. Not gradually, not steadily, in an avalanche. The proto-Jupiter was essentially vacuuming up everything in its vicinity, growing at a rate that would have added several Earth masses per century. Within just 3 to 4 million years of its initial formation, Jupiter had reached approximately its current mass, 318 Earth masses. More than twice the mass of all other planets in the solar system combined. Recent research from Caltech, published in 2024, revealed something even more remarkable. At this point in its history, roughly 3.8 million years after the solar system's first solids formed, Jupiter was actually significantly larger than it is today. As the young giant contracted and cooled over the following billions of years, it shrank to its current size of about 86,880 miles in diameter. But in its youth, Jupiter may have been nearly twice as large, with an even more powerful magnetic field extending far into the surrounding space. But here's where the story takes a dramatic turn. Jupiter didn't just sit quietly in its birthplace, growing fat and happy on the abundant gas of the solar nebula. No, Jupiter went on a journey that would reshape the entire solar system. Scientists call this the Grand Tack hypothesis, and if it's correct, it explains one of the greatest mysteries of planetary science. The mystery is Mars, or rather, the mystery is why Mars is so small. You see, when scientists run computer simulations of how planets form in the inner solar system, they consistently produce a Mars-sized planet, except their Mars is far too big. According to the models, Mars should be roughly the same size as Earth or Venus. But the real Mars is tiny, just 1/10 the mass of Earth. Something stunted its growth, and that something many scientists now believe was Jupiter. Here's what they think happened. As Jupiter grew to its enormous size, it didn't stay put. The gravitational interactions between the young giant planet and the surrounding gas disk caused Jupiter to begin migrating inward toward the Sun. This is called Type 2 migration, and it's a well-understood process that we've observed in other solar systems throughout the galaxy. The gas disk acts like a kind of gravitational brake and accelerator combined, transferring angular momentum between the planet and the disk. Jupiter began moving inward, slowly at first, then faster, past the frost line, into the region where rocky planets would one day form. According to the Grand Tack model, Jupiter migrated all the way into about 1.5 astronomical units from the Sun, roughly where Mars orbits today. Along the way, it was a cosmic bulldozer. Its gravity scattered planetesimals, destroyed protoplanets, and generally wreaked havoc on any material in its path. The inner solar system was swept nearly clean, but Jupiter's inward journey didn't last forever, because something else was happening out in the cold reaches of the solar system. Saturn was forming, and when Saturn grew large enough, it too began migrating inward, chasing after its bigger sibling. But Saturn was moving faster than Jupiter. Eventually, the two giants were captured in what scientists call a mean motion resonance, a gravitational dance where Saturn completed exactly 3 orbits for every 2 orbits of Jupiter. This resonance changed everything. The combined gravitational influence of the two giant planets, locked in their orbital dance, reversed the direction of migration. Instead of continuing inward toward the Sun, Jupiter and Saturn began moving outward, away from the inner solar system, back toward their current positions. This reversal, the tack like a sailboat changing direction, is what gives the Grand Tack hypothesis its name. As Jupiter retreated outward, it left behind a depleted region, the zone between about 1.5 and 4 astronomical units from the Sun. This region, robbed of much of its original building material by Jupiter's passage, would never be able to form a large planet. The material that remained would eventually coalesce into something small, something stunted, something we call Mars. Meanwhile, the debris that Jupiter scattered during its inward journey didn't simply disappear. Some of it was flung outward beyond the frost line, where it contributed to the building materials of the asteroid belt. Some of it was scattered inward, toward the regions where Mercury, Venus, and Earth would form. This cosmic reshuffling may explain why Earth has water. The The water ice that condensed beyond the frost line was transported inward by Jupiter's gravitational stirring, delivering the liquid that would one day fill our oceans. Jupiter's wild youth sculpted the entire architecture of our solar system. In 2025, research from Rice University provided even more evidence for Jupiter's formative influence. Using state-of-the-art computer simulations, planetary scientists Andrei Isidoro and Bibhav Shrivastava showed that Jupiter's rapid early growth created rings and gaps in the protoplanetary disk, similar to the structures we now observe around young stars with the ALMA telescope in Chile. These gaps delayed the formation of certain types of meteorites by millions of years, explaining a mystery that had puzzled scientists for decades. But Jupiter's influence didn't end with the Grand Tack. Hundreds of millions of years later, the giant planet would trigger another cataclysmic event, one that left scars across the entire inner solar system. Scientists call it the Late Heavy Bombardment. Roughly 700 million years after the solar system formed, the inner planets were suddenly subjected to an intense barrage of asteroid and comet impacts. The evidence is written on the face of the Moon, where ancient impact basins like Mare Imbrium and Mare Serenitatis date to this violent period. Earth, Venus, and Mars bear similar scars, though erosion and geological activity have erased much of the evidence on our own world. What caused this sudden bombardment? Many scientists believe the answer, once again, is Jupiter, along with its fellow giant planets. According to the NICE model, named after the city in France where scientists first developed it, the giant planets underwent a second period of migration hundreds of millions of years after their initial formation. During this migration, Jupiter and Saturn may have crossed another mean motion resonance, this time a 2-to-1 resonance, where Saturn completed exactly one orbit for every 2 orbits of Jupiter. Crossing this resonance destabilized the orbits of Uranus and Neptune, sending them careening outward into the primordial Kuiper belt, a vast region of icy bodies beyond Neptune's current orbit. The gravitational chaos scattered countless comets and asteroids inward, bombarding the inner planets with a rain of cosmic debris that lasted for hundreds of millions of years. The late heavy bombardment may have had profound consequences for life on Earth. Some scientists believe it delivered additional water and organic compounds to our planet. Others argue it sterilized the early Earth, repeatedly wiping out any primitive life that had managed to gain a foothold. Either way, Jupiter's gravitational influence was once again reshaping the destiny of worlds. But Jupiter's role in shaping our solar system extends beyond these ancient cataclysms. Even today, 4.5 billion years after its formation, the King of Planets continues to exert its influence in ways both subtle and profound. Consider Jupiter's gravity. With a mass 318 times that of Earth, Jupiter is by far the dominant gravitational force in the solar system after the Sun itself. This gravity acts as both a shield and a threat to the inner planets. On one hand, Jupiter deflects many comets and asteroids away from the inner solar system, potentially reducing the frequency of catastrophic impacts on Earth. On the other hand, Jupiter's gravity can also redirect objects toward the inner planets, increasing the impact rate. The debate over whether Jupiter is Earth's protector or its enemy has raged among planetary scientists for decades. Computer simulations have produced contradictory results. Some suggest that without Jupiter, Earth would be bombarded by comets 10 times more frequently. Others indicate that Jupiter actually increases the impact rate by gravitationally focusing asteroids and comets toward the inner solar system. The truth is probably somewhere in between. Jupiter both helps and hurts, depending on the specific trajectory of any given object. What we do know is that Jupiter's presence has fundamentally shaped the distribution of small bodies throughout the solar system. The asteroid belt, located between Mars and Jupiter, exists in its current depleted state largely because Jupiter's gravity prevented a planet from forming there. The Kirkwood Gaps, empty regions within the asteroid belt where no asteroids orbit, mark locations where orbital resonances with Jupiter would have made any orbit unstable over millions of years. The Trojan asteroids, meanwhile, represent the opposite phenomenon. Regions where Jupiter's gravity actually stabilizes orbits rather than disrupting them. These asteroids cluster around Jupiter's Lagrange points, locations 60 degrees ahead of and behind the planet in its orbit, where the combined gravitational influence of Jupiter and the Sun creates stable gravitational wells. Thousands of Trojan asteroids have been discovered, and NASA's Lucy mission, launched in 2021, is currently en route to study several of them up close. Now let's journey to Jupiter itself, to explore this magnificent world that has played such a central role in our solar system's history. Jupiter is big. That simple statement doesn't begin to capture the scale of this planet. If Jupiter were a hollow sphere, you could fit more than 1,300 Earths inside it. Its diameter is 11 times that of Earth. Its mass is greater than all the other planets, moons, asteroids, and comets in the solar system combined, multiplied by 2. And yet, for all its bulk, Jupiter is remarkably insubstantial. Its average density is only about 1.33 grams per cubic centimeter, barely denser than water, and far less dense than rocky planets like Earth. If you could somehow find an ocean large enough, Jupiter would almost float. This low density reflects Jupiter's composition, roughly 76% hydrogen and 24% helium by mass, with traces of heavier elements like carbon, oxygen, nitrogen, and sulfur. Jupiter has no solid surface in the traditional sense. As you descend through its atmosphere, the gas simply becomes denser and denser, eventually transitioning into a liquid without any clear boundary. This liquid hydrogen, compressed by the tremendous weight of the atmosphere above, takes on strange properties deep within the planet. At depths of about 13,000 miles below the cloud tops, the pressure becomes so extreme, millions of times the atmospheric pressure at sea level on Earth, that the hydrogen is squeezed into a metallic state. Metallic hydrogen is one of the strangest substances in the universe. It conducts electricity like a metal, yet it's made of the lightest element on the periodic table. Scientists have struggled to create metallic hydrogen in laboratories on Earth, achieving it only briefly under extreme conditions. Yet within Jupiter, there exists an ocean of this exotic material larger than some planets. An ocean that generates the most powerful planetary magnetic field in the solar system. Jupiter's magnetic field is almost 20,000 times stronger than Earth's. It extends so far into space that if you could see it with your naked eye, it would appear larger than the full moon in Earth's sky. This magnetic field traps charged particles from the solar wind, creating intense radiation belts that would be lethal to unprotected astronauts. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, received radiation doses that gradually degraded its electronics over the course of its mission. The magnetic field also interacts with Jupiter's moon Io, the most volcanically active body in the solar system. As Io orbits within Jupiter's magnetosphere, the rotation of the magnetic field generates powerful electrical currents that flow between the moon and the planet. These currents carry about 2 trillion watts of power, enough to supply the entire United States several times over. They create auroras at Jupiter's poles that dwarf anything seen on Earth, with some auroral displays releasing more energy than the entire electrical output of human civilization. But perhaps the most famous feature of Jupiter is not its magnetic field, nor its size, nor even its moons. It's a a storm that has been raging for centuries. The Great Red Spot. The Great Red Spot is an anticyclonic storm, a high-pressure system, in Jupiter's southern hemisphere. Winds at its outer edges blow at speeds exceeding 400 miles per hour, circling the storm center in a counterclockwise direction. The entire system rotates once every 6 Earth days, carrying clouds of ammonia and other compounds around and around in an endless vortex. How big is the Great Red Spot? At its largest, measured in the late 1800s, it was approximately 40,000 kilometers across, large enough to swallow 3 Earths side by side. Today, it has shrunk considerably, measuring roughly 16,000 kilometers in width. But it remains the largest storm in the solar system by a wide margin. The discovery of the Great Red Spot is itself a story worth telling. The first person to clearly observe and document a large oval feature on Jupiter was the English physicist Robert Hooke, who reported seeing it in 1664. The following year, Italian astronomer Gian Domenico Cassini observed what he called the permanent spot, using powerful new telescopes made by Giuseppe Campani of Rome. Cassini tracked this spot for years, using its movement to calculate Jupiter's rotation period, approximately 9 hours and 56 minutes, remarkably close to the modern value of 9 hours and 55 minutes. Cassini's observations of the Great Red Spot mark an important milestone in the history of astronomy. By tracking the movement of this feature across Jupiter's disk, Cassini pioneered techniques that are still used today to measure the rotation rates of planets, moons, and asteroids throughout the solar system. In recognition of his contributions to the study of giant planets, NASA named its Saturn mission the Cassini spacecraft. But here's a mystery that has puzzled astronomers for centuries. Is the Great Red Spot that Cassini observed in the 1660s the same storm we see today? The historical record is frustratingly incomplete. Cassini and other astronomers tracked the permanent spot until about 1713. Then, for over a century, there are no clear observations of a similar feature. The Great Red Spot that we observe today was first definitively recorded in 1831 by German amateur astronomer Samuel Heinrich Schwab and has been continuously observed since 1878. A 2024 study of historical observations suggests that Cassini's permanent spot may not be the same storm as the modern Great Red Spot. If so, the current storm is only about 190 years old, still ancient by Earth standards, but a mere infant compared to Jupiter's 4.6 billion-year history. Alternatively, the original storm may have persisted but simply went unobserved during the 18th century, when interest in planetary astronomy temporarily waned. We may never know for certain. What we do know is that the Great Red Spot is changing. Throughout the 20th and 21st centuries, astronomers have watched it shrink. In the 1970s, when the Voyager spacecraft flew past Jupiter, the Great Red Spot was still about 25,000 kilometers wide. Today, it's roughly 2/3 that size, and the shrinkage appears to be accelerating. Some scientists predict the spot could become circular by 2040, if current trends continue. Others wonder if it will disappear entirely. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has provided unprecedented insights into the Great Red Spot structure. Data from Juno revealed that the storm extends far deeper into Jupiter's atmosphere than anyone expected, approximately 300 miles below the visible cloud tops. This makes the Great Red Spot not just wide, but also surprisingly tall, more like a cylinder than a pancake. Juno also discovered that the Great Red Spot is fed by warmer air rising from beneath, helping to explain how it has persisted for so long. Unlike hurricanes on Earth, which derive their energy from warm ocean water and quickly dissipate over land, the Great Red Spot has no land to cross and no ocean to deplete. Jupiter's atmosphere is essentially infinite, providing an endless supply of energy to drive the storm's circulation. But the Great Red Spot is far from Jupiter's only storm. The planet's atmosphere is in constant turmoil, with thousands of smaller storms, vortices, and jet streams circulating at various latitudes. The distinctive bands that give Jupiter its striped appearance, the dark belts and light zones, are actually alternating streams of atmosphere moving in opposite directions. Where these streams meet, turbulence and storms form along the boundaries. Some of Jupiter's storms are white rather than red. Astronomers call them white ovals, and several have been observed since the 1930s. In 2000, 3 white ovals that had existed for decades merged into a single, larger storm. Over the following years, this storm gradually turned red, earning the nickname Red Spot Jr. or, more formally, Oval BA. Scientists believe the color change occurred as the storm grew powerful enough to lift material from deeper in Jupiter's atmosphere, where chemical reactions with sunlight produce the reddish compounds that color these features. The chemistry behind Jupiter's colors remains one of the planet's enduring mysteries. The hydrogen and helium that make up most of Jupiter's atmosphere are colorless. The browns, oranges, and reds we see must come from trace compounds, perhaps sulfur, phosphorus, or complex organic molecules created by lightning and ultraviolet radiation. But despite decades of study, scientists still cannot fully explain Jupiter's palette. What about Jupiter's interior? For decades, scientists assumed Jupiter had a relatively simple structure. A small, dense core of rock and metal, surrounded by shells of metallic hydrogen, liquid hydrogen, and gaseous atmosphere. But data from the Juno mission has challenged this picture. Gravity measurements suggest that Jupiter's core is not a compact ball, but rather a diffuse region where heavy elements are mixed throughout a large volume of the planet's interior. This fuzzy core may extend halfway to Jupiter's surface, fundamentally changing our understanding of how giant planets are structured. One possibility is that Jupiter's core was disrupted early in its history by a massive impact. Computer simulations suggest that a collision with a planetary embryo roughly 10 times the mass of Earth could have scattered Jupiter's original compact core, mixing heavy elements throughout the planet's interior. If such an impact occurred, it would have released tremendous energy, briefly making Jupiter shine almost as brightly as a small star. Now let us turn our attention to Jupiter's family, the remarkable collection of moons that orbit the king of planets. Jupiter has at least 95 confirmed moons, making it the planet with the most known natural satellites in our solar system. But among these many worlds, for stand out above all others, Io, Europa, Ganymede, and Callisto. These are the Galilean moons, named in honor of the Italian astronomer who discovered them more than 4 centuries ago. In January 1610, Galileo Galilei turned his newly improved telescope toward Jupiter. What he saw changed the course of human history. Around the bright disk of the planet, he observed for small points of light. At first, he thought they might be stars. But as he watched over successive nights, he realized these points were moving, orbiting around Jupiter like a miniature solar system. Galileo's discovery was revolutionary. At the time, most educated Europeans believed in the Ptolemaic model of the cosmos, which placed Earth at the center of the universe with all celestial bodies revolving around it. The existence of moons orbiting another planet provided direct evidence that not everything in the heavens circled Earth. Galileo rightly saw this as powerful support for the Copernican model, which placed the Sun at the center of the solar system. Galileo wanted to name his discovery the Medicean stars, in honor of his patron Cosimo II de' Medici. But the names that stuck came from German astronomer Simon Marius, who independently observed the moons around the same time as Galileo. Marius named them after figures from Greek mythology associated with Zeus, the Greek equivalent of Jupiter, Io, Europa, Ganymede, and Callisto. Each of the Galilean moons is a world unto itself, with unique characteristics that have made them primary targets for exploration and study. Let's take a journey through this remarkable family. Io, the innermost of the four, is the most volcanically active body in the solar system. When the Voyager 1 spacecraft flew past in 1979, scientists were astonished to discover active volcanic eruptions, plumes of sulfur and sulfur dioxide shooting hundreds of kilometers above the moon's surface. Io has no impact craters visible from space. Volcanic material is resurfacing the moon so rapidly that any craters are buried almost immediately. Why is Io so volcanically active? The answer lies in Jupiter's immense gravity and Io's orbital resonance with the other Galilean moons. Io orbits Jupiter in exactly half the time it takes Europa to complete one orbit, and in exactly 1/4 the time of Ganymede. This resonance keeps Io's orbit slightly elliptical, which causes the gravitational pull from Jupiter to vary as Io swings closer and farther from the giant planet. This variation flexes Io's interior, generating tremendous heat through a process called tidal heating. The energy released is equivalent to hundreds of times Earth's total geothermal output. Europa, the second Galilean moon, could not be more different from its volcanic neighbor. Europa's surface is covered with water ice, crisscrossed by a network of brownish-red cracks and ridges. The surface is remarkably smooth with very few impact craters, suggesting that it is geologically young and continuously being renewed. But what makes Europa truly extraordinary is what lies beneath that icy shell. Multiple lines of evidence suggest that Europa harbors a global ocean of liquid water beneath its frozen surface. This ocean may contain more than twice as much water as all of Earth's oceans combined. And where there is liquid water, there may be life. Europa is considered one of the most promising places in the solar system to search for extraterrestrial life. The ocean is kept liquid by tidal heating, similar to what drives Io's volcanoes but less intense. Hydrothermal vents on Europa's ocean floor could provide chemical energy and nutrients, much like the deep-sea vents on Earth that support thriving ecosystems without any sunlight. NASA's Europa Clipper mission, which launched in October 2024, will conduct dozens of flybys of Europa to study its ocean and assess its habitability. Ganymede, the third Galilean moon, holds a special distinction. It is the largest moon in the entire solar system, with a diameter of 5,268 kilometers. Ganymede is larger than the planet Mercury. Like Europa, Ganymede appears to have a subsurface ocean, sandwiched between layers of ice. But Ganymede is unique among moons in possessing its own intrinsic magnetic field, evidence of a liquid iron core similar to Earth's. Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system. Its ancient surface records billions of years of cosmic bombardment, with impact craters piled upon impact craters. Unlike the other Galilean moons, Callisto shows little evidence of internal geological activity, suggesting it was never heated enough to differentiate into distinct layers. Yet even Callisto may harbor a subsurface ocean, induced by Jupiter's powerful magnetic field. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and will arrive at Jupiter in 2031. JUICE will study all 4 Galilean moons before eventually entering orbit around Ganymede. becoming the first spacecraft to orbit a moon other than our own. Beyond the Galilean moons, Jupiter's satellite system includes dozens of smaller, irregular moons. Most of these are probably captured asteroids or comet nuclei, gravitationally snared by Jupiter over billions of years. Many orbit in retrograde, opposite to Jupiter's rotation, and at high inclinations to the planet's equator. These chaotic orbits suggest violent capture events in the distant past. Jupiter also possesses a ring system, though far more tenuous than Saturn's spectacular rings. Jupiter's rings were discovered in 1979 by the Voyager 1 spacecraft and came as a complete surprise to scientists. The main ring is composed of small, dark particles knocked off Jupiter's inner moons by micrometeorite impacts. Unlike Saturn's rings, which are made of bright, reflective ice, Jupiter's rings are difficult to see except when backlit by the sun. Humanity's exploration of Jupiter began in earnest with NASA's Pioneer 10 spacecraft, which launched in March 1972 and made its closest approach to Jupiter on December 4, 1973. Pioneer 10 was the first spacecraft to cross the asteroid belt, the first to fly past Jupiter, and the first to achieve escape velocity from the solar system. Its twin, Pioneer 11, followed in 1974, passing closer to Jupiter and returning even more detailed data before continuing on to Saturn. The Voyager missions of 1979 revolutionized our understanding of Jupiter and its moons. Voyager 1 and Voyager 2 returned thousands of images revealing details never before seen. The churning storms of Jupiter's atmosphere, the volcanic eruptions on Io, the cracked ice shell of Europa, the immense Valhalla impact basin on Callisto. These twin spacecraft transformed Jupiter from a distant point of light into a real place, a destination as compelling as any on Earth. The Galileo mission, which operated from 1995 to 2003, provided the first long-term study of Jupiter and its moons. Galileo orbited Jupiter for nearly 8 years, making close flybys of all 4 Galilean moons and returning a wealth of data about their surfaces, interiors, and environments. The mission included an atmospheric probe that descended into Jupiter's clouds, transmitting data for 57 minutes before being crushed by the increasing pressure. At the end of its mission, Galileo was deliberately crashed into Jupiter to prevent any possibility of contaminating Europa with Earth microbes. If Europa does have an ocean capable of supporting life, scientists want to ensure that any life found there is genuinely native, not hitchhikers from our own planet. The Juno spacecraft, which arrived at Jupiter in July 2016, has provided our most detailed view yet of the planet itself. Unlike Galileo, which focused on the moons, Juno's primary mission is to study Jupiter's atmosphere, interior, and magnetosphere. The spacecraft flies in a highly elliptical polar orbit, swooping close to Jupiter's cloud tops before retreating to a safe distance from the intense radiation belts. Juno's discoveries have been remarkable. The spacecraft revealed that Jupiter's poles are covered with massive cyclones arranged in geometric patterns, 8 storms circling the North Pole and 5 around the South. It measured Jupiter's gravitational field with unprecedented precision, revealing the fuzzy core structure discussed earlier. And it captured stunning images of Jupiter's atmosphere, showing swirling clouds in colors and patterns that seem almost artistic. As we look to the future, Jupiter will continue to be a prime destination for space exploration. In addition to the Europa Clipper and JUICE missions mentioned earlier, China's Tianwen 4 mission aims to send an orbiter to Jupiter and possibly land on Callisto around 2035. Concepts for future missions include submarines to explore Europa's ocean, balloons to float in Jupiter's atmosphere, and even crewed missions to establish a permanent human presence in the Jovian system. Why does Jupiter continue to captivate us? Perhaps because it represents everything that is extreme and alien about the universe beyond Earth. Jupiter is a world of superlatives, the largest, the oldest, the most massive, the most influential. It is a planet that shaped the formation of our entire solar system and continues to affect the orbits of asteroids and comets to this day. But Jupiter also reminds us of how much we still don't know. Why does the Great Red Spot exist, and how long will it last? What lies at Jupiter's center? Could life exist in Europa's dark ocean? Is Jupiter truly Earth's protector? Or is it something more complicated? These questions drive scientists to design new missions, build new telescopes, and push the boundaries of human knowledge ever outward. 4.5 billion years ago, a cloud of gas and dust collapsed in an unremarkable corner of the Milky Way galaxy. From that collapse came a star, and around that star, a disk of debris slowly coalesced into planets. One planet grew faster and larger than all the others. It migrated inward and outward, scattering material, creating gaps, shaping the architecture of the entire solar system. It captured moons, generated magnetic fields, spawned storms that would last for centuries. That planet is Jupiter, the first planet, the largest planet, the king. And its story, like all good stories, is far from over.